This is the second free response question in the electrostatics packet. The question reads, in a television set, electrons are fired through, they're accelerated from rest by being fired through an electron gun. They pass through deflecting plates and then strike a screen. Determine the potential difference through which the electrons must be accelerated in the electron gun in order to have a speed of 6 times 10 to the 7th meters per second when they enter the deflecting plates. Kind of one way of thinking about this is kind of, if I make a sketch here, we would have one negatively charged plate and then one positively charged plate, actually with a really small hole in it here. So I probably made that a little bit big. And so if I drew an electron here, the potential difference between the plates, if this is plate A, we could say it's at a relatively low potential and that this is at a higher potential. And then so basically the electron through that uniform electric field is going to get accelerated and reach some final velocity here of roughly about 6 times 10 to the 7th meters per second. I'm going to use one of the variants of the work equation, so let's take a look. We start with electric potential by definition, difference in potential being change in potential energy per unit charge. And therefore we know that that's equal to negative change in kinetic energy per unit charge. You know, when I'm doing this quickly, I'm going to leave the deltas out. Via the work energy theorem, we know that that's negative work per unit charge. And at this point, I know that the work done is going to be equal to change in kinetic energy. So I think what I'm going to do in this case is multiply, let's go ahead and put it in this form. I'm going to multiply both sides by Q, and then I'm going to get the voltage times the charge is equal to negative work, which is equal to negative kinetic energy, which would be 1/2 mv squared. This is the form that I like. I've got everything that I need here. So the potential difference is what I'm looking for. So I'm going to divide both sides by Q. I'm going to get negative 1/2 mv squared. All of those things are known, divided by Q. When I do that, the potential difference, by the way, this charge is negative 1.6 times 10 to the negative 19 coulombs. The mass is about 9 times 10 to the negative 31st kilograms, obviously really small, and then I have to square this this value of 6 times 10 to the 6 times 10 to the 7th meters per second. When I do all of that, I get about 1 times 10 to the 4th, 1.0 times 10 to the 4th volts. Being my answer here for voltage. Okay, so that's the answer to the first question. And when I go to the second question, we put some focus on the horizontal plate. So it says, pair of horizontal plates shown below is used to deflect the electrons up or down. And then B says, which pair of plates must be at a higher potential for the electrons to be deflected upward? Check the box below and justify your answer. So if the electron has a negative charge here and we want it to deflect up, then the upper plate must be at a higher potential. There must be relatively positive charges up here. That creates an electric field. Don't get confused. The electric field looks like this, but that's if it were a positive charge. That's going to cause an upward deflection like that of the electrons. So the upper plate must be charged, and you can kind of explain that that the charges on the upper plate must be positive, since the electron is negative and must be electrostatically attracted to the upper plate. It then says, consider only an electron's motion as it moves through the space between the plates, and then compute the following. They want to figure out the time that it takes to move the plates. This is just going to be velocity is equal to distance over time. So we have the velocity. It's 6 times 10 to the 7th meters per second, and we have the distance. It's 0.04 meters. That's kind of given to us on that sketch. So we have that information. And so we can just solve for that using the concept of constant velocity. So let me go ahead and write that out. As soon as this stops panning down, it's moving pretty slowly. All right, so now I can say basically that velocity is equal to x distance in the x direction, over time, and I'm going to basically solve for time. So basically time is going to be that x distance, which is 0.04, divided by the velocity, and when I run that through my calculator, I get 6.7 times 10 to the negative 10 seconds. Okay, so there's my answer for the amount of time that it takes to make it through the plates. The second question wants to know the vertical displacement. And so this is a bit trickier. So I'm going to start with force. I need to know the acceleration. At the end of the day, I want to use this. Delta y, which is my vertical displacement, is going to be my initial velocity, but that's in the y direction, which we know is initially 0 plus 1/2 at squared. So if I know the acceleration and I know the time that it's been between the plates, I'll be able to basically answer this question, what's the vertical displacement. So let's go ahead and do that. F is equal to m times a. We also know that the force, the electrostatic force, is equal to QE. This is just another force, another variant of the equation. Remember that that comes from the definition of the electric field is force per unit charge. When I multiply Q times E, that's also equal to force. So I'm going to get MA is equal to QE, and then finally this final substitution, another form or substitution in for E, will be that the electric field can be described as the electric potential difference per unit distance. And so when I substitute that in for the electric field, I'll get something that looks like this. MA is equal to Q times V over D. So solving for A ultimately becomes, I'm just going to divide both sides by M, Q times the potential difference between the two plates, divided by the mass, divided by the distance. And when I plug those numbers in, the distance in this case being that vertical distance between the plates, which is taken from the sketch, 0.012 meters. When I plug those numbers in, I get 6.5 times 10 to the fourth. 6.5 times 10 to the fourth meters is going to be my vertical displacement. Sorry, that's not my vertical displacement. I'm going to calculate that for acceleration. Plug that in here. I know time, which was taken from the previous piece, and then when so I'm basically substituting that term in for A and then solving for delta y. Okay, show that why it's reasonable to neglect gravity. First of all, let's talk about gravity. Gravity, the weight of the electron or the force due to gravity is going to be equal to m times g, where m is on the order of about 10 to the negative 31st kilograms, multiplying that, of course, by the acceleration due to gravity, 10 meters per second, roughly, gives me about, something on the order of 10 to the negative 30 newtons. So that's the force that the Earth is pulling on the electron with. Let's compare that to the force that the electric field is having. So I can write that out as the electric force is equal to Q times the magnitude of the electric field, and we also know that we can write that as Q times the electric potential per unit distance, over the distance. And we get something on the order of about 10 to the negative 14 newtons for the electric field. So, we see here that this is way, way smaller, the gravitational force, than the electric force. Okay, the final question says, still neglecting gravity, describe the path the electron takes after it leaves the plates. If we neglect gravity, the electric field and therefore the electric force acting on the electron is gone, so it's going to travel in a straight line. That's Newton's first law.